Okay, so if this is going to be a solution to star, what does that mean? Right? If it's a solution to a differential equation, that means when you plug it in, it works, right? So we have d dt of e to the lambda t times u. Now, how does that work? Well, you can pull the constant out. You get lambda e to the lambda t times u vector. Does everyone, so do you see how that works? Basically, e to the lambda t differentiates like usual. And if you're differentiating a function times a constant vector, the constant vector just rides along. Maybe you saw this in Calculus 3. What else? So on the other hand, we want that a times u, what's a times u? Excuse me, a times x. Well, that would be a times e to the lambda t times u, right? We want these two things to be equal. So let's write that out. We need to have lambda e to the lambda t times u vector equal to a e to the lambda t times u vector. Do you guys see what I did? I just plugged in our guess into the differential equation. Now, do you see anything we could do? How about e to the lambda t? Is this ever 0? No. So we could divide by that, right? No charge. So this gives us lambda u is equal to au, right? Or, and by the way, by definition, if au is equal to lambda u for u not equal to 0, then we say u is an eigenvector of A with eigenvalue lambda. So what we just have derived is that the only way that apparently I need an eigenvector in order to solve this thing, right? Now let's keep working on this eigenvector thing since it's new to us. So we've got another way to look at this, of course, is au minus lambda u equal to what? I'm just rearranging it, setting it equal to 0, right? And then what we do is we rewrite that as a minus lambda times the identity matrix times u is equal to 0. I is the identity matrix. It's the matrix that has like, what, do you guys know what the identity matrix is? So like I is 1, 0, 0, 1, or that's I2. I3 would be like 1, 1, 1 with zeros everywhere else. This matrix, when you multiply it by another matrix, it just gives you back where you started with. It behaves like the number 1 for matrix multiplication. So I've rearranged our eigenvector condition to be a homogeneous equation, right? And what did we assume about u? Non-zero. So we have homogeneous equation with u not equal to 0 solution, right? And what else? The 0 solution. I mean, if you think about it, if you just plug in 0 here, it also solves it, right? So we have a system of linear equations with 2 solutions. And we're working over the real numbers or possibly the complex numbers. If you've got 2 solutions, how many more do you have? What are the rules for solving linear equations? This you guys should know without linear algebra, maybe. Maybe. It's all in these 3 pictures. You've either got parallel lines, no solutions. You've got skew lines, a unique solution. Or you have the same line. So you either have no solutions, one solution, or infinitely many. Them's your choices if we're working over an infinite field, like the reals or the complexes. Now, if you're working over like Z2 or something, you know, like a finite field with two elements, it's a different story. But if we're in the infinite field context, if we've got two solutions, we've got infinitely many. All right? So more to the point, the determinant of what matrix here cannot be non-zero. I mean, if the A minus lambda I matrix was invertible, we'd be in trouble because the only solution then would just be the zero solution, right? Because you multiply both sides by the inverse of the matrix, you get u equal to 0, which is not what we want, right? So we need that the determinant of A minus lambda I is equal to 0. That is not up for grabs, and this is the so-called characteristic equation. So it's kind of neat. You see the necessity of the determinant being 0 for the characteristic equation contrasted against the need for the determinant to be non-zero for linear independence over here, right? Really different uses of the determinant.
So we're trying to prove that there is no unique solution for this?
Yes, if there is a unique solution, we'd be in trouble because it'd be the zero solution.
Right, okay.
Here, let's work out an example. Where are we? Example 11, 12? I'll make it 12. It just feels better. An even dozen, right? So how about this? X prime equals to 3x plus y. Y prime equals to, I don't know. We'll make this one simple. We don't have much class time left. Let me make it like 2y. All right. Now, admittedly, we don't need the eigens. You could use common sense to solve this one, right? Because you could solve the second one first and then plug it in the first one, solve it, right? So this is a kind of easy problem. But let's solve it with the eigenvector technique. So we go, my A is what? 3, 1, 0, 2. So the determinant of A minus lambda I is the determinant of 3 minus lambda, 1, 0, 2 minus lambda, which is, by the way, 3 minus lambda times 2 minus lambda. This is not surprising. If it's a triangular matrix, right? If it happens to be triangular, whatever numbers are in the diagonal, those are the eigenvalues. So we're now deriving that lambda 1 is equal to 3 and lambda 2 is equal to 2. So those are my eigenvalues. And then I got to find eigenvectors. Let's do it. Which means I have to actually solve. So like lambda 1 equals to 3, I need to solve A minus 3i times u1 equal to 0. What is A minus 3i? So there's the two equations that we should be able to find eigenvectors from. Can you guys solve those? Do you notice anything weird about those 2 by 2 systems that I wrote down? How many distinct equations do you have? Just one, right? It better be the case, right? If it's not the case, then if there's 2 independent equations, you're back to the case of skew lines, you're going to get just a 0 solution. That wouldn't be good because we're looking for a non-zero solution, right? We need non-zero vector. So this basically just tells me that v is equal to 0, u is free. This guy tells me that u plus v is equal to 0. So if I just think for a second, I can put u1 equal to 1, 0. And over here, I can set v equals to -1. Then that would tell me u is equal to 1. So u2 would be 1 minus 1, right? And then following my template, I have x1 is equal to e to the, what was it? 3t, 1, 0, and x2 is equal to e to the, what was it? Oh, 2t, 1 minus 1. So the solution to this differential equation is c1 e to the 3t 1, 0 plus c2 e to the 2t 1 minus 1. That's your general solution in vector format by the eigensolution technique, which is not general. There are matrices which this won't work for. Now, as this sinks in, you should notice that there's great ambiguity in how I chose u1 and u2, right? Like, why did I put 1, 0 there? I could have just as well put what? Like, well, I can't put 0 because that wouldn't be allowed because that would give me the 0 vector, which is forbidden because of what we're after. We're after a non-zero solution, right? But I could just as well have put 1,333,342 or whatever. I mean, I don't know, etc. I mean, what would that do? It would just change the meaning of C1 down here, right? So you're multiplying by constants to adjust for initial conditions. So if you use different vectors here, it just corresponds to a relabeling of your constants in the solution. It's not a big deal. So how do you choose vectors then? Well, I say you choose them whichever way is easiest. For me, that means whole numbers, no fractions. For you, it might mean whatever comes out of your Texas Instruments calculator, or there are nice web tools to calculate eigenvectors for matrices online. Yeah. So anyway, we'll be on this eigenvector technique the whole next class. I just wanted to get us started on it. Al, shut up. You can turn off the thing. Let me give you back.